consider the following problem, which is find the field theta over the domain omega such that the divergence of Q minus some source term equals 0, where Q is a flux, standard flux, or minus conductivity, gradient of theta. The conductivity is dependent on the field theta, so K equals theta, and the source term also depends on the field theta, is minus 6 theta. So that's just that's the problem that I need to solve. I need to find theta basically defined over the entire domain that satisfies that, and I need boundary conditions. To make it simpler, I'm just going to have a purely Dirichlet problem, so all the boundaries have essential boundary conditions, and that's just because I want to avoid calculating integrals over the boundary for now. So that's the problem that I need to solve, right? This is a well-defined boundary value problem. How do we solve this with FE, right? The first question would be get the weak form. This is the standard. We've done this one already, so that will end up with, find our theta over C0 with theta equals x squared on gamma theta, and such that the integral of Q, so this one will be minus the integral of Q dotted with the gradient of the shape function, minus the integral over omega, minus the integral of SW over omega equals 0. And there's no boundary integrals here because I have no natural boundary conditions. Otherwise, I would have the extra term, plus the integral over the boundary, gamma or delta omega of the things that have, if I were given a normal flux, I would have to be integrating that as an extra term. For all W's in Z0, and this should be in C0, in C0 over omega, C0 omega. That's correct notation. So yeah, with W equals 0 on the boundary. So that will be my weak form, right? Now, given the weak form, let's do discretization. So I need a mesh, right? Essentially, I need a mesh, so I'm gonna do what I did before, which is I'm gonna define the mesh that I defined in the previous video. So I'm not gonna go over the details, but I need some mesh, right? Where I need some nodes and some elements. So these are my nodes and these are my elements. 1, 2, 3, 4. So elements and nodes. And I'm not gonna write it out because it's the same mesh as I used in the in previous lecture notes for today. But I discretized it, right? So once I have the discretization, then for every element, I have the discrete residual well, let me do it in parts. So for every element, I first have I forgot to mention the linearization of the weak form. So I have the weak form, and I also have linearization of the weak form. Maybe I should write that out. Actually, so sorry about this, because I need it here. So I also need linearization in the direction of some increment, right? So that would be the linearization of this in the direction of some increment. And that one we have done before, but that one will be minus the integral over omega of, instead of q, I need the derivative of q with respect to the increment times the, well, in this case because there's a gradient, so this will require linearization of q which is a function of theta in the direction of the increment there with the gradient of w, and then minus, and then here we need the linearization of s, which is could be a function of theta in the direction of the increment times w. And I've done this requires specific knowledge of what the s and what the q look like, and I've done it for just one simple example, but in the general terms you will have to linearize, so let's just keep it there. Okay, so now I discretize. Now for every element I have the residual over the element is going to be similar to the integral that I've done before, but only evaluated over the element. And then if you remember, what I did is when you actually plug in the definition of w as the sum of the weighting functions times the null values, only the weight functions end up in the residual. So in the residual, this will look like q dotted with gradient of the shape functions. So let me, instead of saying the entire vector, so the component A of the residual will be, because there's the gradient of the th basis functions. So because for every element here there is 4 basis functions, so the residual has 4 entries, right? Where each entry corresponds to one value, one shape function. Then so that one actually with a minus, and then minus integral over the element of s times, again, in the initial weak form there's a w. Once you plug in the discretization of the w as the sum of the shape functions times the null values, then the only thing that survives here is the shape function. So that gives you, for every value of a, so this will be for a equals 1, you get gradient of shape function 1 and shape function 1. If you calculate the integrals, that goes into here, and then a equals 2 is the second entry, a equals 3, and a equals 4. So that's how you get this 4x1 vector. And then you also get the entries AB of the tangent, and we've done this one for the specific case of the what is the actual linearization of Q. So this one is still somewhat general. The residual is somewhat general. For this one, for the K, because I need to do the linearization, let me just remind that Q equals minus K gradient theta. And K depends on, K is actually theta, right? And then S equals minus 6 theta. So that means that the linearization of Q in the direction of the increment theta is going to be minus 1 minus increment theta gradient x of theta, right, minus theta gradient x of the increment. So that will be the linearization of Q, and the linearization of S in the direction of the increment is just minus 6 increment. So those will be the linearization. And then similar to the W, once you plug in the fact that the increment, we want the discrete increment, so again, null values times shape functions, you take the null values out, and the only thing that survives is the shape function. So when you end up here, it's going to be linearization of q, which is this, minus integral of omega e, linearization of q, which is minus increment, but as I said, once you plug in the definition of the increment as sum of shape functions times nodal values, and you take the nodal values out, this one will just leave a shape function in. So shape function b times gradient x theta times gradient of NA minus, so that minus theta, and then gradient of the increment. Again, when I plug in the definition of the increment as shape functions times nodal values, I'm going to end up with gradient of NB, right? And that times gradient of NA. Because this part right here is only linearization of Q, I still need to multiply by this gradient of NA. All right, so that would be from this part right here. This is just linearization of Q, and that's from the linearization of Q. You can see that we get these shape functions for B. So that would be one part of the integral, and then the other part of the integral is minus integral over omega e of linearization of S. Well, linearization of S is minus 6 increment. So minus 6, and the increment, like I said before. So once you plug in the increment, the discrete increment, which is the sum of shape functions times the nodal values of the increment, and you take the increment out, you end up with just the shape functions. So here I'm going to end up with shape function B times shape function A. So that one I still have. So this is linearization of S times my original shape function A. And that's it. So that would be my tangent. It clearly has indices A and B because I have the shape functions, original shape functions that I had before, which corresponded to the to these weighting functions, and now I have new shape functions which correspond to the increment for the linearization. So these will go into this 4x4 matrix. So this one is a 4x4 matrix where the first row, the columns are, this will be B equals 1, B equals 2, B equals 3, B equals 4, A equals 1, A equals 2, A equals 3, A equals 4. So for example, for this one right here, if you plug in shape function B equals 1 and 1, you end up with, and you calculate the integral, that will end up in this entry, and so on. So basically just plug in the different values of the A and B, so basically evaluate the corresponding shape functions in this integral, and that will give you this 4x4 matrix. Hopefully that is kind of clear. So just recapping very quick, I gave you this strong form of the problem, which is find some temperature field that satisfies some PDE with some boundary conditions. In order to solve this with the finite element method, first thing is to go from the strong form to the weak form. I'm skipping all the steps, but hopefully if you go back, you can see how you do that. We will need also the linearization. So if you do the linearization in terms or in the direction of some increment, then you would have to find what is the linearization of Q and what is the linearization of this source term. I have them below. All of this is still continuous, but we'll have to introduce some discretization. We have done this for the quadrilateral elements. We have a mesh, and then once you have a mesh, then you have the residual and the tangent for every element. The residual is obtained from the weak form once you plug in the fact that the W equals the sum of the shape functions times the nodal values. So once you plug that in, which comes from the fact that you have discretized with these shape functions, and you take the nodal values of the weighting function out, you end up with just shape functions in those integrals, and then the q and the s. And because, for example, for the quadrilateral element, there's 4 different shape functions, so there's 4 different integrals that you can calculate, one for each of these shape functions, and you put that into this 4x1 vector. So now you want to do this might be nonlinear, so you want to solve it with Newton-Raphson iterations, and you need to linearize q and s, right? So here I have the linearization of q and s in the direction of some increment. And again, similar to the weighting functions, when you introduce the fact that the increment is, again, sum of shape functions times the increment, nodal increment values, then, and you take those out of the integral, and you end up with just the shape functions. So here I have the linearization in the general terms, in terms of the increment, this delta theta. But then when I put it into the integral, I sort of get rid of the nodal values, and I just end up with shape functions, right? So instead of increment theta, I'm going to end up with shape function b. Instead of gradient of the increment, I end up with gradient of the shape function. And now, because I still have the shape functions a, which corresponded to the weighting function, which defined my residual. And now I have these shape functions b, which appear because of this linearization in the direction of the increment. So now I have choices for a and b. So if you evaluate this integral right here, for the different a and b combinations, there's 16 combinations. So 4 values of a, because we have 4 shape functions, 4 values of b. You can fill out this 4x4 matrix. Good. And so then what we just did in last class, so, once you have a loop, once you have REKE, for all elements, you can assemble your global residual and global tangent, either the entire one or just the one that has the degrees of freedom, so R star and K star. And then how do you solve for the theta? You need a Newton-Raphson, right? So Newton-Raphson. How do you do that? Initial guess for theta, and then your next iteration is going to be your previous iteration minus K star at the previous iteration times the residual, which may depend on the value, right? So if it's nonlinear, then the stiffness and the residual change for every iteration. This is just the initial guess, and then just do this loop until convergence. And that's it. Once you finish the loops, you end up with basically the theta values that are the solution for that system. Yeah, that's it. That's the whole solution. So hopefully that makes sense. I have a Python notebook for this, but this is what I wanted to do, is sort of like put everything together now, finally, right? So we have the strong form, and then we end up with a solution of a possibly nonlinear system. All right, so just one more video, last one for today, and it's a Python.